Hello everybody, welcome back to Monte Carlo Methods. In today's video, we're not actually going to advance the Monte Carlo story. Instead, this is going to be what I've begun to call fill the gap videos. So if you see parentheses FTG after one of my video titles in a series, that means that it's a piece of mathematics or statistics that we're going to need to go forward, but not actually a topic specific, in this case, to Monte Carlo methods. Today's fill the gap video is going to be about covariance, which we need in order to compute the variance of a sum of random variables. Sums cannot just be pulled out of variances unless they're independent, and in the next video, we're going to be working with some random variables that are not independent. So if you're okay with computing a variance of a sum by using covariance, then move right along. You don't need this video. But if you'd like to learn how to pull sums out of variances, then stick around. Covariance is a measure of association between two variables. So let's say I have two random variables, capital X and capital Y. They have their own distributions, their own means, their own variances. Let's talk about the means. There is an expected value for X and an expected value for Y. We usually use the Greek letter mu for expectations, but because there's two of them, I'm going to use mu sub X and mu sub Y respectively. With this notation, we are ready to define the covariance between these two random variables. We're going to denote it with a COV of X comma Y, and it is defined to be the expected value of X minus its mean quantity, and then multiplied by Y minus its mean, and that's it. So that is a theoretical quantity, and I hope to make sense out of it for you by first looking at a sample version of this. Imagine some realizations of the two random variables X and Y. They have some kind of joint distribution. I mean, they could be completely independent, but in this video, they're probably going to have some kind of joint distribution that describes how they operate together. And if I actually simulate some pairs of random variables and plot them in R2, I might see something like this. When we want to get an idea about a true mean of a distribution that we call mu, we look at the sample mean X bar. And in this case, I want to get some idea about what the covariance means, which is a theoretical quantity involving expectations, by looking at a sample version of it. So the expected value of X minus its mean times Y minus its mean, that is a probability weighted average. And let's look at the actual sample mean version of this. For this video, I'm going to assume that mu sub X and mu sub Y are known, so we don't have to substitute sample means. And I'm going to add them to the graph like this. And I have broken up this graph into 4 quadrants. So let's focus on the upper right one first. For all the points up here, the X coordinates of these points are above the mean for X. So the quantity X minus mu X is positive for all these points up here. The same thing for the Y coordinates. The Y coordinates of all these points are above the mean for the Y's. And so Y minus mu Y is greater than 0 for all the points up here. So if you look at X minus the mean for X times Y minus the mean for Y, we've got two positive numbers multiplied. That is positive, and we're going to put values like that into an average. Again, trying to estimate the expectation, which is a probability weighted average with some kind of real average. Now let's look at the points down here in this quadrant. Down here, all the X values are below their mean mu X. And the same thing is true of all the Y values. And this means that the quantity X minus mu X is negative, and so is the quantity Y minus mu Y. But the product, the negative times the negative, is a positive number. So when you think of including terms like X minus mu X times Y minus mu Y, and actually sampled values and throwing them into an average that is supposed to be approximating that expectation, which is a probability weighted average, the points down here are going to contribute positive values in a sum we're forming to compute an average. In these other two quadrants, it's not hard to convince yourself that each X coordinate minus mu X times the corresponding Y coordinate minus mu Y is going to be negative. So if you think of averaging all of these products, we're going to add up a lot of terms, and most of them are going to be positive. All these terms coming from the points up here are positive, All the terms coming from the points down here are positive. And then we have a few negative terms that are going to go into the sum. But overall, we expect this kind of average, which is a sample average, to be positive. And in fact, the covariance between x and y, which is a probability-weighted average of terms like this, is going to likely be positive if your sampled values look like this. That is, if when one variable, say x, is increasing, the other variable y is also increasing, those variables will have a positive covariance. It's very likely they will. So we're looking at sample values here. It's kind of like saying, is the true mean mu going to be positive just because a sample mean is positive? That's not exactly going to track, but the idea here is to sort of get a handle on the true covariance looking at a sample covariance. A sample covariance, an average of terms like this here, is going to be positive. And so typically for a positive true covariance, you're going to see some kind of picture like this. Some kind of, as one is increasing, the other is increasing. So if we flip these around, now I've got the case where if one is increasing, the other is decreasing. And if you break this up into 4 quadrants based on where mu x and mu y is, you can see that up here I've got very few points, and over here I've got very few points. Most of the points are here and here. And in here and here, the x, well, let's go to this one first. So in here, the x-coordinate is below its mean, but the y-coordinate is above its mean. This means that x minus mu x is negative, but y minus mu y is positive. So the product x minus mu x times y minus mu y is negative. Also, for these points down here, that sort of product is negative. So if you think of averaging all of these, you're going to have mostly negative values and very few positive values. And this sample covariance that you would get by actually taking these realizations and forming these products and computing that average is going to be negative. So when you see something like this, it is likely that the true covariance, that expectation that doesn't come from the sample, is something negative. Indeed, if the covariance between x and y is negative, that means that as x increases, y decreases, or vice versa, you have this inverse sort of relationship. This isn't just any sort of relationship here. Specifically, covariance between x and y measures a strength of a linear relationship. So if you sort of imagine a line going up through these points or through this, we are looking at really nothing to do with the slope, but how tightly clustered these points are around a line of any particular slope, as long as it's not 0 or infinite. Let's look at one more picture. If your x and y coordinates in your sample give you sort of just like a roundish cloud and you don't really see an increasing or decreasing relationship, the covariance here is likely to be very close to 0. So we've got this idea of positive covariance, negative covariance, and a covariance close to 0. But in terms of magnitude, these covariances can be very, very spread out. So you can have very, very large covariances or very small ones in both directions. So large magnitude, small magnitude, positive and negative. And I do want to spend one slide talking about correlation, only because I want to use the word uncorrelated as it relates to covariance. But we're not actually going to need to compute correlation in this course, or at least not in the next video. The correlation between x and y is defined to be the covariance between x and y divided by the product of the two standard deviations. So sigma x is the square root of the variance of x, which is sigma x squared, and sigma y is the square root of the variance of y, which is sigma y squared. These are both positive square roots by definition, and this covariance is positive or negative, but we can do a lot of icky algebra to show that this quantity now is between -1 and 1 inclusive. So you're going to get +1 for the correlation if your x and y points follow an exact line with some positive slope. It doesn't really matter what the slope is, but you are very tightly clustered and actually lying on a line. And the correlation between x and y takes on the value -1 if your x and y coordinates are following precisely on a line with some negative slope. So now we have an idea of what is a large number and what is a small number, because we can't get above 1 or below -1. But again, we don't really need correlation for this course. I just wanted to point it out for a term, because look at this expression up here. the correlation is zero if and only if the covariance is zero. And so if the correlation is zero, we say that X and Y are uncorrelated. We're going to see that this is different than saying they're independent, but we also now know that if the covariance between X and Y is zero, the correlation is zero, and we say that X and Y are uncorrelated. So this is the last I'm going to say about correlation, at least for a while. If the covariance between X and Y is zero, we say that X and Y are uncorrelated, and it's really because it relates to this correlation expression. So let's look at some properties of covariance and maybe different ways to compute it. First of all, if we look at the covariance of X with itself, by definition, this is the expected value of X minus its mean times X minus its mean. This is the expected value of X minus its mean all squared, and that is precisely how we define the variance for X. Just like the variance was first defined as an expected value of X minus its mean squared, but then manipulated into maybe a more computationally pleasing form of the expected value of X squared minus the expected value of X all squared, we have something similar to say about covariances. Expectation is a linear operator, so I'm going to write out this covariance and multiply this out. I'm going to run the expectation through. Now keep in mind that mu sub X and mu sub Y are constants, so they can be pulled outside of expectations. And this last term is the expected value of constant, which means you can drop the expectation. It's kind of like saying the expected value of 3 is simply 3. You don't need the expectation. So note that this is mu X and this is mu Y. So once you fill that in, you've got a bunch of products of mu X, mu Y. You've got a negative mu X, mu Y, a negative mu X, mu Y, and a positive mu X, mu Y. And when you add them all together, you get a single negative mu X, mu Y. In other words, the covariance between X and Y can be computed as the expected value of X times Y minus the expected value of X times the expected value of Y. If X and Y are independent, the expected value of a function of X times a function of Y will factor into the two individual expectations. Now this could be fill-the-gap material, but it's kind of getting a little crazy at this point. So check out a MathStat course if you need to go deeper into this. But if you're computing the expected value of X times Y, that's going to be a double integral or sum in the discrete case of X times Y times the joint PDF for X and Y. And if they are independent, that will factor into the marginal PDF for X times the marginal PDF for Y, and you'll have a double integral and you could move things around, and you will eventually see that if X and Y are independent, this expectation becomes basically this over here, and the covariance is 0. So independent random variables are uncorrelated or have 0 covariance, but the other way around is not necessarily true. So I can make up some dependent random variables that are just sort of balanced just right so that this is 0, but they are dependent. So remember, that only works one way. Independent, covariance is 0. Covariance is 0, maybe independent, maybe not. It's easy to see using this definition that the covariance is symmetric in X and Y. That is, the covariance of X and Y is the same thing as the covariance of Y and X because you just flip these two terms in a product. Suppose that A is a constant, not a random variable. We do know the expected value of A times X is A times the expected value of X. With that, we're ready to look at the covariance of A times X and Y. This, by definition, is the expected value of A times X minus the mean for A times X, which is actually A times the mean for X. And that whole thing gets multiplied by Y times mu sub Y. And I can factor A out of this guy in here, and then I can pull that outside of the expectation because expectation is a linear operator. And then what I'm left with in here is the covariance between X and Y. So we have shown that for a constant A, the covariance of A times X and Y is A times the covariance of X and Y. Similarly, we can pull a constant A out of the second term. So the covariance of X and A times Y is A times the covariance of X and Y. You can either prove this in the same way, or you can just claim symmetry. You can flip them around and pull the A out of the first one if that feels better to you. but the same thing is going to happen. So a constant here or a constant here can be pulled out in front of the covariance, and it doesn't come out squared like it does in the variance case. What happens if we have a constant in front of both of these? So if we want to find the covariance of a times x with b times y, we can pull both constants out to get a times b times the covariance of x and y. So this is where that square comes in the variance calculation. If you want to compute the variance of a constant a times x, you can write this as the covariance of a times x with a times x. You can pull both a's out front, so you get a times a out front, or a squared, and you're left inside with the covariance of x with x, which is the variance of x. So this is another way of showing, outside of using the definition of variance, this is another way of showing that constants pull out of variances squared. Now we're going to see that you can pull sums inside and outside of covariances. Suppose you have 3 random variables, x, y, and z, and in all of these cases, these random variables could be discrete or continuous. The expectations, if they're discrete, are computed with sums, and integrals if they're continuous. So let's find the covariance of x plus y with z. By definition, by the original definition of covariance, as opposed to some of the other expressions we've come up with, this is the expectation of x plus y minus its mean, and I'm going to call that mean mu sub x plus y, times z minus its mean, which I'm going to call mu sub z. Now, mu sub x plus y is the expected value of x plus y, but expectation being a linear operator, this is the expected value of x plus the expected value of y, which is mu sub x plus mu sub y. So I'm going to replace this with mu sub x plus mu sub y. And now I'm going to regroup these terms so that I have x minus mu x plus y minus mu y, and then that whole thing times z minus mu z. Now I can multiply this out by keeping things grouped. I've got the expected value of x minus mu x times z minus mu z plus y minus mu y times z minus mu z, and I can run the expectation across onto each of those two terms. And here you see the covariance between x and z, and here you see the covariance between y and z. So look what we did. The covariance of x plus y with z is the covariance of x with z plus the covariance of y with z. And of course, we can start here and go back to here. So this is saying that I have a sum inside the covariance, and it's becoming a sum outside the covariance, or vice versa. Now, we also have this on the other side. Similarly, or using symmetry, so we can show it the long way, or we can use symmetry and say we've already shown this. But if you want the covariance of x with the sum y plus z, this is going to be the covariance of x with y plus the covariance of x with z. So finally, and the last thing in this video, kind of short, is we want to generalize this sum going inside and outside the covariance and constants being pulled out of the covariance in order to compute the variance of an expression like this. The sum as I goes from 1 to n of a constant a sub I times a random variable capital X sub I. We can write this as the covariance of this sum with itself. Now, in either of these sums, I is just an index. We're running over all I. So to avoid confusion, I'm going to change the index in the second sum to j all the way across. I really haven't changed anything. It's the same sum. And now you can imagine the sums inside becoming sums outside. We get to pull both of these sums out front and also pull the constants, the ai and the aj, out front. And we're left with this expression. So we want to compute the variance of a big fat sum with constants in front. If they're independent, we can just run the sum through and pull the constants out squared and do sort of the stuff you may be more familiar with. But if they're not independent, we can rewrite it as this covariance term. If xi and xj are independent, and that happens when I is not equal to j in an IID sample, this covariance between xi and xj is going to be 0 whenever I is not equal to j. So a whole bunch of these terms are going to be 0. The only surviving terms are going to happen when j is exactly equal to I. In that case, we'll get the covariance of xi with xi, which is the variance of xi. And in that case, you're going to get an a sub I and an a sub I. So You may have to write this out on your own paper, but you can see that if the xi's are IID random variables, this variance can be written as a sum of the AI squared times the individual variances. And identically distributed means all those variances are the same, so you can plug in whatever that common variance is. But we're going to get a lot of practice with this, so that's all I have to say for this video. In the next video, we are going to do a test of independence. We're going to use it to test our random number generator, but we can use this for a random sample from any distribution. If your goal is to produce IID, independent and identically distributed random variable realizations, then you would like them to follow the right distribution. We've been making these histograms and matching them up with PDFs, but you would also like the subsequent values or the consecutive values to be independent. And I find that very hard to believe using a random number generator that is an algorithm. But remember, the good random number generators can fake independence pretty well. So in the next video, we're going to do a hypothesis test for independence of our sequence of random variables that we're going to observe through simulation. I hope to see you in the next one.